We're here today to present on a solar panel for a residential customer, or solar system rather, for a residential customer. This project is done by 4 members of this team, myself, Hogg, Andre Richards, Everton Mackenzie, and Jeremy Wilson. So let us go into it now. The design of this project completed as a part of the requirement for the port's electrical drives and machine. Now, in order to size a system of this magnitude, one first has to go into what the customer is going to require. Now, what we do here is to find out the customer's essential load and non-essential load to come up with what the total requirement will be for a day. Now, as you can see here, we have the lighting, TVs, laptop, refrigerator rather, as the essential loads, while the non-essential loads are washing machine, microwave, blender, etc. Now, when we added all the power for the day, we get a total of 373 watt. 7,000 rather, 373 watt. And the watt hour is 11,572.5 watt hour. Now, in order to size the PV array, the panel efficiency is 75. This efficiency is the rated efficiency of the panel, how much sunlight they can gather out of the total sunlight that will be coming into the panel. After taking into account all the losses, the solar energy insolation on the panels is 6.00 watt per meter square. The standard service factor of 1.2. Now, in sizing the array, is simply the desired energy in watt hour times the service factor times the sun hour per day times the efficiency of the panels. So as you can see here, it is the watt hour that was in the table above times 1.2 service factor, the sun hour per day times the efficiency, which gives us a total of 3,086 watt. Then we go into now the number of panels, which is the solar array that we just calculated, divided by the power of the solar panel, or the rating. The rating here is 230 watt per meter square. And when we divide that, we get 13.41. But 13.41, we don't have 13.41 panel. So therefore, we round it up to 14. This also gives us a leverage of oversizing, which will go well for the process. The inverter sizing, it is recommended, standard recommendation, that the inverter size be 125 to 130% of the total watt of the appliances or the system. Therefore, it is then calculated that the inverter size will be then the watt that is needed for the day and 1.3, which will give us 9,584 watt. The charge controller, because we want a steady charge on our batteries, right? And we need to also put this into the system to have steady flow charge. This will also help with the lifespan of our batteries and so forth. When we go about sizing our charge controllers, is that we know that the module, the PV module is a 24 volt, 230 watt, and the short circuit current from this would be 10 amp. Here we can see how we calculate the short circuit current. It is the 240 divided by the voltage, which will give us 9.58, which we round up to about 10%. And the number of strings is 7. So therefore, to calculate the rate of the charge controller, the number of strings times the short circuit current and the system efficiency, and there we go, is 93.3 amps. Now I now move over to Mr. Mackenzie, who will come and explain the system layout and also go into the efficiency of the system. Mr. Mackenzie.
Thank you very much, Mr. Philip Huck. Now, what I'll be looking at is the layout of the system and also looking at the system's efficiency. Now, as you can see on screen, we have a schematic layout using blocks for the entire PV system. Now, immediately here now we have the PV arrays. Now, these PV arrays is what is going to be capturing the sun's light. And it's going to be used, this is basically what's going to initiate the process. So the sun's light is going to be captured here. Then the combiner is essentially like a bus bar which connects all of the PV panels together. Now we are looking at the protective devices here now. We have a ground fault protector and a DC breaker. From this part now we go to our inverter / charge controller. And what happens at this point is that the PV arrays is going to be charging the batteries through the charge controller. So we have a battery bank down here and also a breaker to protect the batteries. And once these batteries are filled, the charge controller now switches over to operating using the PV panels only. So it's going to be supplying the load through the main panel using the sun's energy. Now this would happen during daylight. Now at night, when we no longer have sunlight now, the process would switch over to the battery bank, and the battery bank now would have been feeding through the inverter. At this point here, you have direct current. So what the function of the inverter is to do is convert from direct current to alternating current. Now this is what you're going to be using to feed the load. Now to look at the system's efficiency, we are going to be looking at the major components and the efficiency of those major components that we have making up the system. And the major components we are referring to are going to be the PV array. Those are the photovoltaic cells. We're going to be looking at the efficiency of the inverter, and we're looking also at the efficiency of the battery. Now, first of all, looking at the efficiency of the battery. The batteries that we use in our system design is the Trojan L16 deep cycle batteries. And these batteries have an efficiency ranging from between 85% to 95% efficiency based on the manufacturer specs. For our calculation now, we use an optimum value of 95%. The inverter we chose was the Xantrex Hard Freedom inverter. And inverters are generally very efficient. They normally convert most of whatever power comes into them. This inverter here is rated at an efficiency of 97%. Now, the least efficient of the major components now, however, are going to be the PV array. Now, this PV array has a low efficiency, mainly because most of the sunlight which goes onto the surface of the panels is going to be reflected away instead of being converted to electrical energy. It also has a thermodynamic efficiency in which most of the heat which now absorbed into the photovoltaic cells are not going to be converted to electricity. That efficiency is about 85%. Now, the efficiency of the system now, it could be looked at in two aspects. One aspect when you're operating only on a battery bank, and another aspect when you're operating using the PV arrays. Now, if you look at the efficiency of the system now, you can see it right here. Whenever you're operating on battery bank only, the efficiency of that system is going to be a function of the efficiency of the inverter and also the efficiency of the battery bank itself. This gives an overall system efficiency of 92.15%. Now, whenever you're operating using PV arrays, the PV arrays are very inefficient, and as we said, this is due to most of the energy, the sun's energy being reflected away. The PV arrays normally have an efficiency of about 41%. Now, this is going to drop the entire system efficiency down to a low value of 37.78%. But this doesn't mean it's a horrible figure, because remember we are just trapping the sun's energy, which we have an abundance of, and we are converting it to electricity. Now, to look at battery sizing, I turn over to Mr. Jeremy Wilson.
Yes, thank you, Mr. Mackenzie. Now, after we've captured all of this energy from the sun, where do we put it? It has to be stored in a battery. Now, how do we size our battery? Now, for our Trojan L16 deep cycle battery, it is used to store energy, DC energy from the solar panels, and the battery is rated at 24 volts, 240 amp hour, and has within a 2-day of autonomy and 85% efficiency. Now, the battery sizing is done by calculating the energy consumption times the days of autonomy divided by the efficiency times the discharge percent times the voltage. Now, this works out to be a value of 2,836.4 watt per hour. Now, how do we determine the number of batteries that we need to supply this energy for 3 days of autonomy? Now, this is done by using the battery sizing divided by the battery rating. Now, our battery size was the 2,836. We divided by the 240, and that gives us a value of 11.8. But we can't use 11.8 batteries, so we have to run this value up to 12 batteries. Now, how do we come up by the choice and the suitability of the battery? Now, batteries are divided into 2 ways. One, by their application and by their construction. Now, the major construction types are flooded, gel, and absorbed glass matte. Now, normally the battery used in photovoltaic circuits are solar or lead acid deep cycle batteries. Now, deep cycle batteries can be discharged and recharged continuously. They are compatible with systems that need long-term energy and are suitable for various applications, but mostly for solar. Now, the absorbed glass matte batteries are more suitable for storage as they are more resistant to degradation and can store energy for a longer period in time. Now, and normally as well, the AGM batteries require little maintenance and there is no need for ventilation, and they will not spill any liquid as they are absorbed glass matte. They are also typically lighter and cheaper and less than other forms of batteries. Now, the other factors in choosing batteries is the amp hour. Now, this is the amount of current you can get per hour from these batteries. Now, the temperature and humidity is another important factor in choosing your batteries. They are critical in storage of batteries. In fact, battery capacity ratings are usually specified at about 77 degrees Celsius Fahrenheit. As batteries get colder, their voltage drops and performance reduces. Now, another important to consider is how deeply you discharge your battery once you switch over now to your inverter to supply the household. Now, by specification, your depth of discharge should not go below 50%. And this value lower than that will derate the battery and reduce its ability to deliver current over a period of time. Now, to go on to how the system works, I will now hand over to Mr. Andre Richards.
Afternoon, viewers. Now we look at how the system works. Alright. Our system, as described earlier, is designed to sustain 11,572 watt power per day. So, therefore, to provide this rated power, we need to use a PV panels, 14 PV panel rated at 230 watt to provide this wattage for the system. As explained earlier, the PV panels, this is what provide the DC source. It captures the PV panel, convert the sun's energy to the direct current needed to supply the DC to the system. So therefore, as the diagram before, as you see, the panels are connected to a combiner box. What this combiner box does is to take the take the number of PV panels and put them in, connect the wires them to one box and send out a main cable. This main cable provides a DC source and send it to a charge controller. In our system, we specified a 96 amp charge controller. What this charge controller does is basically a voltage and a current regulator to keep the battery from overcharging. Skip. No. Alright, the charge controller. What the charge controller does is two main functions the charge controller does. What it does is take the DC current from the PV panels and use to charge the battery throughout the daytime, and as well as provide the DC source to the inverter to supply the system throughout the day. So therefore, what the charge controller does is it charges the batteries in the day, and while the batteries are fully charged, it switches over and uses the voltage sent to the inverter and power the system. Right? So therefore, the inverter now, we use a 10,000 watt inverter, a 24 volt pure sine wave, to convert our DC current, DC volts, to the AC volts needed to supply the household. And we move on. So now we look at our material list and costs. Well, as you know, with all this system put into place, we need to observe our material list and total costs needed. So we look at some of our main equipment used in the system, which is the Zantac E-Freedom inverter, 10,000 watt 24 volt. It is cost $4,000. All these prices are quoted into US. So as you can see, our deep cycle battery, the 12 deep cycle battery needed at a unit price of $335, give us a total of $4,020. Other small equipment in there, miscellaneous equipment needed, and therefore, as you can see in this table above, all this of price and material needed to set up the system. All this total to a $17,193.9 US. And as I say, these prices quoted into US. Skip that. So now, as you can see, the costs are quoted into US dollar, and therefore we convert this US dollar into our Jamaican currency used here in Jamaica, and at a rate at $102 Jamaican to 1 US, and we basically get a 1,753,777.8 Jamaican. And our labor costs, as you know, setting up a system of incorporate our labor costs, and the labor cost is 25% of this figure here in Jamaica, which we get a total of 3,300, which is Jamaican 438,400. So this gives our project a total cost of $2,192,222.25. As you can see, this is basically figure here. This figure is basically what we needed to supply a system to independent run and supply voltage to our resident. You understand? Yeah. So our payback period, you know that when we design a project, we need to know what our payback period looks like. And from our payback period, we use the average kilowatt hour per month, which is 321.5 kilowatt hour average per month the client use. And therefore the client will use a total, no, this is per month, yeah, and therefore the client will use a total of 3,858 kilowatt per year. So we use our JPS rate 10, that is rate 10 for a residential house. And at rate 10 for the first 100 kilowatt, it is $6.35. And for the next energy is $14.52. Our fuel and IPP charges is $26.54. So for this client, the typical monthly bill will calculate to be $8,532.61. dollars per month. Well, this is basically in Jamaicans now. So the total monthly bill now, the 8,532.61 equal.
The IP and fuel.
Including the IPP fuel and the one up and the first 100 kilowatt, a total of 12,832.79 GCT not included. So as you can see, this is our monthly calculation at the average kilowatt used per month. So now we move, therefore, condition remain constant. The client will pay approximate value of a Jamaican 148,606.48 per year. That's our energy, that's our yearly bill. So we use this figure here to divide our cost for the system, and we get a total of 14.7, which is equivalent to around 15 years. So basically this system will take 15 years to pay back for itself, and so forth. And well, we did not incorporate maintenance costs as well as inflation. So this is just a rough estimate of what the payback period will be like. So move on. So this comes to the end of our presentation here, and well, and thanks for viewing. Thank you.